Our first speaker for this afternoon is Jianqing Fan from Princeton University, and he's going to talk to us about challenges of high-dimensional classification and feature selection.
Okay, thank you, Dennis. I just arrived a few hours ago, and I start to like it here, and it's great pleasure. To talk to so many experts here. And after my talk, you may say, "Oh, wow, it's so simple." And actually, that's what I meant to be simple. Okay. So here's the outline. I'll talk about challenge of dimensionalities. I'll talk feature selection, and then a special feature selection plus number of feature selection we call feature annealed independent rule, so we abbreviate as a FAIR. And then we'll talk about numerical studies. And whatever I talk at the beginning, I'll also talk, honestly, the problems. So I'll talk about further extension and some study that we are currently working on. Okay, so challenge of high dimensionality. So high dimensionality categorizes many contemporary statistical problems. So in bioinformatics, if you want to do disease classification using microarray proteomics or fMRI data, you'll easily get into, let's say, 20,000, 40,000, tens of thousands of input features. So in, let's say, documents or text classifications, like, for example, whether some of those communications have national security concerns or not. So the feature space can be also very large. And one of the most annoying things that we get each day is like email spams and so on. And then, of course, classification can be applied to other kind of machine learning work, such as voice recognition or handwritten recognition and so on. So in the high dimensional, in the high dimensional problems, so there are always two major concerns. One is computational cost, and the other is estimation accuracy. And so this is just very similar. I use an analogy here. Similarly, to like if I want to visit Peter Biggle at Berkeley. So there are two ways you could do this, right? So one is I take a flight from New York to San Francisco and then drive to Berkeley. And so this is a large scale, and then followed by a small scale. Certainly, it will be computationally very fast, and economically, it's very, cheap. And the other way, people just say, okay, let me just modify existing procedures, and just like driving a car. You have a very nice car, and you'll end up with at Berkeley, but certainly your computational cost, it'll take you time and also cost more. So this is the features. Of course, it's very difficult. When we do scientific investigation, which scale are we in? Are we in the scale of making a plane, or are we in the scale of making the different kind of cars? So, to me, many of our procedures that we are currently in use, at least is in the same scales, whether it's lasso or other methods, panelized method, they are in the same scale of computational cost and estimation accuracy. So my talk today, hope, is to give a very simple way that bridging this, but of course not everybody has to agree that that's what I'm doing. Okay, so let me focus on high-dimensional classification. So one of lovely observation by Biggle and Levina basically says that the Fisher discriminant, which is really the nearest centroid, in Mahalanobis distance, perform poorly, due to diverse spectra. So, Biggle and Levina basically says that if you connecting the first centroid in the high-dimensional space and the second centroid in the high space, so you form a direction. If that direction happen to fall in the worst direction, that is the largest, the eigenvector correspond to the largest eigenvalue occurrence matrix, then you may have problems of doing that. And also, in high dimension, imagine if I do like a protein-protein interaction. I have 5,000 proteins and times another 5,000 proteins. So I got 25 million, coherence matrices. 25 million by 25 million coherence matrices. Certainly, we have trouble of even implementing this in a high-dimensional case. So they suggest that that you could solve this problem by using what's so-called the independent rule, which is really like a Nye-based rule. You just ignore the correlation in this coherence matrix and just put diagonal there. So you got that. And in the paper that we did ourselves, we basically showed that even independent rule behave like a random guess, and our observation is due to a different thing from Peter and Biggle and Levina, which basically says due to noise accumulation. So imagine I have 20,000 dimensions. I have to estimate the centroid of each coordinates of 20,000. When I aggregate those together, I'll get accumulation of noise. So unless signal is strong enough, I mean, the noise accumulation will overwhelm the signal accumulation. And how to quantify this? So before we talk about how to quantify this, let me just make a very small, simulation example. So in this example, I have 4,500 dimensions, and I have 100 sample size from training from class 1 and another 100 from class 2. And the second centroid I take as a 0 origin in this 100 dimensional space. And the first one I take 98% as 0 and 2% as double exponential distribution. So if you like to compute what is the maximum noise, I think maximum noise is about that size. So this is one of realizations of the first centroid, mu1, which has about 90 of those are non-zeros. Okay, and this is one of extreme, I think realizations that apparently my student use. So for example, in this direction they have about 5 standard deviation above 0, and this is 4 standard deviation above 0. So if there's an oracle tell you which direction to use, certainly I just use in this direction and this direction. These two directions together would be very, very powerful. And here is indeed what we did. So if I use those two right directions and projecting data in these two directions, certainly, you could separate these two classes easily, or if you even just using one of those, you could nearly separate those. So now if I add in, in this case, I'm adding 998 noise directions, that is adding those directions that doesn't have any discriminant power, because the signal is strong enough. In this situation, signal here is very strong. It's strong enough, of course, I add in 1,000 dimensions. It's still separable between two classes. So if I add in 1,998, so now, in this case, you don't have any discriminant power between these two classes. And we tried the same thing, like, okay, for 45,100 dimensional space, I take a random direction and project data on one random direction, and taking data project at the another random directions. And you can see that, there's no discriminant power either in this direction or in this direction. And in fact, that we showed that in high dimensional space, given the data, and this is the linear, the linear classifier. So for almost all linear classifier in high dimensional space, so it's behaved like a random guessing. So here, the randomness comes from the direction that I take in. So direction, if I randomly, so with probability, with measure 0, measure 1, that all directions that you are chosen given data. So there's no discriminant power. So this basically shows that, essentially shows that in high dimensional space, it is necessary to choose a low dimensional feature. And just like, this is not really a discouraging result, just like a rational, all rational number has measure 0, doesn't mean that there's no good numbers for us to use. The same thing here, we say almost all classifiers in high dimensional space, if you project your data in the direction A, so it all behave like a random guess. And here is one example I show you, and I'll show you later on using other numerical examples. Okay, so now in order to understand the impact of dimensionality, so let's do a little bit very simple mathematical work. So let's assume that I have Gaussian data with centroid mu1 for the first class, centroid mu2 for the second class in p-dimensional space, and they share common covariance matrix sigma, and the independent rule is just this, right? Mu1 minus mu2 to estimate centroids. And this is the average of two centroids. And this is the diagonal matrix of your covariance matrix. And now, if you are asking what is the misclassification rates for x coming from class 1, So you are computing this given data. Since this is a linear rule, so it's just a normal data. So this is very easy to compute that the error rate is 1 minus normal distribution times this psi, and psi is given by here. So now by looking at this, we can easily see that as dimension goes larger, so this guy usually getting larger because this is adding more and more directions. But on the other hand, as dimensionality goes larger, so this is really like a chi-square distribution with degree of freedom p. So therefore, as dimension grows larger, so you also get a noise accumulation with dimensionality p. So let's compute the worst classification error. And here, the parameter space is that the distance, weighted distance between two centroids is at least bigger than Cp. P is the dimensionality. And the maximum of the maximum of correlation is less or equal to some constant. And in addition, that minimum minimum variance is bigger than 0. So here, basically, Cp is measure the strength of signal as dimensionality p increases. And later on, we actually regard this as as you see, later on we'll regard the result here as an orthogonal choice of features. So the first result is more complicated than that. But for presentation, I just say that. If dimensionality is no more than exponential to power n, and if this mathematical condition holds, then the misclassification rate is converge improbably to these guys. And the important for us is not to really see the results precisely, but just to see the impact of dimensionality. So if we can see that the rates here, C0 here, depend on Cp divided by square root of p, right? So the impact dimensionality clearly is exemplified in this factor. As dimension increases, so the two centroids getting further and further in terms of distance, unweighted distance. So and as dimensionality increases, it's also increased with square root of p. So so it's also the noise accumulation also increased with square root of p. And if at certain directions they are very sparse or they are nearly noise directions, so you'll accumulate noise without increasing signal. So it's necessary to choose. It is necessary to choose the dimensionality. And then the second result is just a formality to show what we really says above. So if the average of the spectra is bounded, and the average of square spectra is no bigger than order p, then this and the signal is not way too strong at dimension, then almost all linear classifier. So the randomness coming from A sample at uniform distribution in p-dimensional space would be like a random guess. So all these, these two results really shows it is necessary to even each features contribute some power, discriminant power. It's still necessary to choose choose the feature and to choose the number of features to maximize the discriminant power, because it is not always correct that the higher the more the feature you use, the better the result you'll get. Okay, so here's the feature selection, and in the ideal world, what we really want, let's say we do a microarray and we do disease classification. So ideally, among 20,000 or 40,000 genes, I hope that I will able to choose a subset, let's say 26 genes in this example, so that the class one may look like this, and class 2 may look like this. Okay, so and here I have like 26 genes here. I have 10 patients from class 1, 10 samples from class 2. So if we were able to do this, then of course very nice for future microarray experiments. So what we really, patients come in and we got this these outputs, and we ask ourselves which class does it belong to. So which one? Right, class 1, right? So because there's red here, green on this one, and similarly, so if I have another patient coming looks like this, you'll say it's coming from class 2. So now the question. So from this example, we certainly not only we need to have high discriminant power, but we also really want to understand the molecular mechanism. So we really don't want to like use 20,000 genes, even all of those genes have some discriminant power. Even all of those have high discriminant power. It's not necessarily what we really want to use. We really want to choose a subset so that we could understand the biological mechanism of the study. Now the question at statistical level we are asking is which gene to select and how many should we use? Should we use 26 or should we use 15, and which one to select? So among all those pictures I show you here, you are already seeing something that there are many subsets who have a very high discriminant power. But among the sets that we are choosing here, usually we say marginally there are differences. For a given gene here, one gene here, the class 1 and class 2 are different. For a given gene here, class 1 and class 2 are different, and so on. So this actually suggests us that the picking genes or ranking genes by using, for example, a test statistics. So this is one of the most naive and the most popular one people use in, let's say, high dimensional gene selection is two-sample t-test or any other test you like. And so what is the result of two-sample t-tests? So we basically show the following. So if the dimensionality is no more than n to power 1/3, so gamma is all the way up to 1/3, and if the number of signals that are non-zero elements is no more than power n to 1/6, and so if your let's say the distance between two centroid for the particular gene or particular feature is a little bit a little bit further away from 1/3, then there exists an x looks like this, which is half of 1 gamma, so it's 1/6 rate, such that you could perfectly separate these two classes. So there exists such an x, so that the minimum of signal one would be bigger than x, and the maximum of noise one would be less than x. So you could be so in other words, this is really give a selection consistency. That is, when signal bigger than n to 1/3, so you are perfect. There exists one boundary that you could perfectly separate those two, and at these rates I just mentioned a few minutes ago, and those kind of results rely on the large deviation theory on the two-sample t test statistics. But this doesn't. This basically saying that it's possible, as long as signal is bigger than n to 1/3, you are able to separate signal from noise. But this doesn't mean that you really need to use all those S dimensions, because as we said before, even if as we said before, even if each dimension contribute a little bit, after a while, some of those some of those signals are so weak or so faint, so that noise accumulation may be even bigger. So even if you are able to separate noise from signal, you still need to select a feature and rank the feature. And now the question people may ask, why we are using the two-sample t-test. So one feature two-sample t-test doing here is what I would call independent learning. That is, you decide whether a gene should be selected or not based on itself merits, without referring to any other genes or any other features. So this is and I would like to point out that actually two-sample t-test is really a special version of we call sure independent screening. And since Michael Jordan, the first talk I attend, use so many learning, so I'm taking liberty to call myself a correlation learning. So there are manifold learning. Like my optimization people call optimal learning. So there are many learning, so I added myself a correlation learning. Okay, so you'll see why I'm called correlation learning. So suppose that I have y, which is the response variable. I have let's say 10,000 features. So this is a linear model with let's say 10,000 features, and among those, many of those are 0. So p is bigger or equal to n. And so in the paper, manuscript still by myself and my former student Jianqing Fan at University of Southern California, So we basically says that let's do ranking a feature by marginal correlation. So let me compute the correlation between y and x1 and y and x2, y and x3, and so on. So I'm ranking the important by marginal correlation. And at the end of the day, so I got the ranking of my features. So now in this particular case, if your y is positive 1 and negative 1 for classification, then you could easily see the correlation between y and x. I mean, each feature is really just like n1 the centroid, the first one, n2 centroid divided by standard deviation of that. So in other words, the two sample t-test when n1 equal to n2 is one version of correlation between positive 1 and negative 1 with x. So two sample t-test is one, I mean, like example of correlation learning. And the reason I call correlation learning because I rank in the important according to the marginal correlation with y's. Okay, so in other words, two sample t-tests. So if when response is positive 1 and negative 1, sample size n1 equal to n2 is a special, I mean, version of correlation learning. Now you may ask yourself why we are doing marginal correlation and what is the rationale of doing that? It's so simple. Certainly, it's not consistency. I mean, why we are doing this and. And here is the reason. So for in high dimensional situation, so like 20,000 dimensions, so I mean, or 10,000 dimensions, and I have sample size, let's say 100 or 200 here. So the first thing that you are really worrying is the variance, right? So in order to reduce the variance, you naturally do what we call rich regression. Okay, so this is the rich regression estimator. And since you are so worried about the variance, so you would say, okay, let me reduce the noise as much as I can. So in this case, so you choose a very large lambda. So now ranking the estimator by this, I mean, rich regression is the same as ranking by lambda n times this, right? So the ranking, it doesn't change. The absolute value doesn't change by renormalize it. So as lambda go to infinity, so it's equal to the, the marginal correlation between x and y. So in other words, the marginal correlation estimator between x and y is really a rich regression with rich parameter, take as large as you can because you're so afraid of the noise. So, so in the procedure that Lu and I were doing, so we basically suggesting a very simple what we so-called sure screening. So you have 10,000 feature p dimension here. So you just you just pick the first. Let's say n or n minus 1 or n divided by log n. So you just pick the largest or the most important n feature, or most important n divided by log n feature, and then so this basically rescale the problem from a very large to a moderate size of problem, and we were able to show that there are some so-called sure screening property. That is, under some kind of mathematical assumptions. So among these 200 features you select, all important features are in your model. So here is really the sure independent screening results that let me just explain a few briefly. So we basically said that if you factor x into, let's say it's an elliptical contour distribution with this, and let's say suppose the true model is sparse, and dimensionality is no more than exponential to a certain power, and the matrix satisfies what so-called concentration properties of which is satisfied by Gaussian random matrices. So let me not talk about this, a bit technical, but let me just looking at the other two conditions that have more statistical meaning. So the minimum signal should be bigger than n to a certain kappa, and the maximum of this sigma, the covariance matrix, should be eigenvalues no more than n to power tau. And in addition, we assume that the correlation between the features, right, these are the features, and the y should be bigger than some constant. And this is always the case if all the features, important features here are I mean, if all important features in this matrix are uncorrelated, then this is identical or equal to 1. So this is correct. So if we have this, so that is the minimum. Here is the minimum signal, and here is the maximum of the eigenvalue of the covariance matrix. And if I just choose, so if I choose the largest correlation ranking, let's say choose largest n gamma n. I mean, the most important gamma n features. Then we says that as long as the theta bigger than this number, which depend on the signal that you have. I mean, the weaker the signal, the more, I mean, the feature you need to choose, right? And the larger the tau, the more feature you need to choose. So as long as I choose the number of features big enough, then with probability going to 10 to 1 exponentially fast, the true model is in your selected submodel. So this is called the, sure screening property. That is, with probability, overwhelming probability, the true model is in the submodel. So going back to this picture, so we basically says that if you rank according to using correlation learning, using the correlation to rank the features, and so you just choose the largest, let's say, n features, then under the mathematical condition that we given below, then all important features should be in this subset. Okay, so in practice, certainly you would choose like a dimensionality d equal to n minus 1 or n divided by log n. And the reason you are asking why you are not choosing bigger than n, because given n data points, you cannot identify more than n parameters. So this is the reason. And of course, under mathematical assumption, if I assume 2k plus tau less than 1, actually we have some justifications why you need to choose this. Okay, so now let me talk back to classification problem again. So this is on the feature anneal independent rule, so fair. So again, these are the two questions we are asking. Which feature should I use and how many? And as I said before, even all relevant features are correctly identified by using two sample t-tests or using sure screening procedures. The choice, using all the relevant features is not necessarily optimal because on one hand, you'll contribute to the distance between two sample choice. On the other hand, you also accumulate noise. So one of ideal ranking is according to the, let's say, this is really according to the distance between two sample choice for the jth feature divided by its noise. So this would be the Oracle ranking. And so now this will be Oracle procedure. That is, you're ranking the feature according, if I decide to use independent rule, so the Oracle ranking will be ranking the distance between, for the jth feature divided by its noise. So it's like a t statistics. And now without Oracle, so you mimic Oracle by using just say, okay, let me just keep all the features such that the t-test statistics is bigger than certain threshold. And now the question is, what is the number of features I should choose? So we basically choose the number of features that maximize the upper bound of error rate. So if you look at the theorem 1 again, actually in this case, theorem 1 become really what I have before here. It really become an Oracle choice. Suppose that we are ranking the feature, Oracle ranking the feature from according to the marginal magnitude, that the distance between each features, and I just use the first M feature or the first P feature. So this is really the Oracle's misclassification rates, and if I write really more carefully, I know this is a little bit jumping here because it's just so many. So if I write more carefully, actually, really all the feature I'm writing there is this. Okay, so this is really the upper bound of the error rate, which is depending on the maximum of largest eigenvalue for the M features of correlation matrix using M features. So this is our M, and you may ask him for justifications. And the easier way to see this is in the case that both are identity matrix, so just to make everything normalized. And in this case, independent rule certainly become the nearest centroid rules. And then, of course, if you apply theorem 1, you could easily see that this is the misclassification rates. And the misclassification rates depending on dimensionality in this fashion, which is the signal accumulation to the first m dimensions divided by the square root of dimensionality. So the way that we are, the choice m we make is really to maximize the error rates. So it's the error rate. So this choice may not necessarily optimal among all linear independent rules, but nevertheless give a reasonable justification. Now, how does this procedure compare with Argo? So suppose there's an Argo tell you that I assume all noise are equal to 1. So therefore, the ranking is according to the distance between each features. So if there's an Argo, so Argo choice would be just say, okay, let me just pick all those features at least bigger than certain threshold A. And let's assume without loss of generality is the first m feature are the most important features. And now if you are mimicking the Argos, you just say, okay, let me keep all the features such that my estimated difference between two centroids for the jth feature is bigger than certain constant b. Then you could show that what is the price you pay for, the price you pay for mimicking Argo is reflected in this term here. M is the number of features that you use here. B is the the threshold that you use. So in the case the m times b is small, so if it's sparse enough, m times b is small, then you can mimic Argo very well. Otherwise, you cannot mimic Argo very well. So let me give a few numerical results just to illustrate the points that I just said, and I quickly go to the extension part. So in this numerical example, I have 45. Again, I have 45 100 dimensions, and I sample 30 from class. For class 1, and I have training sample 30 from class 2. And the signal again is 98% 0 and 2% from double exponential distribution. And so this is another realization of this mu1. So the amount around 90 of those mu's are not 0. And epsilon ij are correlated, and we are doing correlated by using what's so-called 4-factor models. So that within the first class they share one common factor, within the second class they share another common factor, within the third class they share another common factor, and then this one is the common factor shared by all 3 classes, and Z here are independent. So each of these are a little bit detail of constructing correlated features, but basically it's following like 3-factor models or 4-factor models in this situation. So now in the simulation we do 100 simulation, and each simulation I have 400 testing sample, 200 from class 1, 200 from class 2. So therefore I'm able to compute the misclassification rates for among those 100 simulations. And here's the result. So if I rank the feature according to 2 sample t test, so as dimension increases, so the discriminant power actually increases. So misclassification rates become smaller. As dimensionality increases, the misclassification rates increases. And so on. So if you, this is just a zone part of this picture. So from here it's clear that even though in this situation the ideal choice should be 90 features, but actually in practice, because it's not really 90 features that optimal. Actually, the optimal number of features probably is around 20. 20 features probably is optimal. So what the minimum misclassification rate maybe is around here, so it's about 1.3%. So this is ranking features by using 2 sample t test, and so this is the ranking the features by using Argo. That is, in the simulation I know which one has a further distance, so I rank according to the Argo, and so this is so you also see the similar phenomenon that as dimensionality grows, the misclassification rates misclassification growth, and this part is the first 80 dimension of this picture. So so the maximum classification rate is if I use all features is 25%, and if I decrease the let's say if I decrease the signal here by half, of course then I will increase maximum classification error to 50%. So this is the same as I mean as the mathematical result that we've shown, and in these 100 simulations, if I randomly project my 4,500 dimension data in one random direction, and I do classification 100 times, so you could see that misclassification rate is around 50%. Indeed, misclassification rate is around 50%. So we do. So this is consistent with the theorem that we've shown that if you take a direction at random in high-dimensional space, and you do classification according to projecting data according to that direction and do classification, then it behaves like a random noise. And we also compared this with nearest centroid method of Tipshirani and his collaborators. So the only difference here between nearest centroids and our method FAIR is the selection of number of features, because we are all ranking by two sample t-test, and so the difference is that we are using the upper bound to choose number of features, and upper bound with classification error to 2, and near centroid using the cross variation to choose number of features. So if we see those pictures, I mean apparently that the FAIR, I mean, tend to be more stable than near centroid methods, and among 100 simulations, so our average number of features is 29, that's 24, and here's the misclassification rate together with that associated standard deviation among 100 simulations. And of course, you could apply these two different data sets and compare further, but of course, for real data, it's always difficult. I mean, to say which one is correct, which one is wrong. So, for example, in this case, I have like a 38 training sample, 27 from one class, 11 from the other class, and the testing I have 20 from one class, 14 from the other class, and here is the training error, and here's the test error, and here's the number of genes selected, and so on. So, of course, you could compare further and so on, apply to different data sets. Of course, you have different type of stories, and so on. So probably that's not that helpful, at least for this purpose of talk. So let me just skip those. So let me talk about the problems I have talked with. So further extension. So so the problem that I have is in the regression situation. So here's the problem. Suppose the x2, let's say x9, highly correlated with x1. Okay. So suppose they are highly correlated with x1, and x2 is let's say independent with all those x1. So by here, through the correlation between x2 and x1, x2 and y will have higher correlation between x2 and between y and x100. In other words, this important variable will be put in rank of 100th, right? Because of correlation between x2 and x1 will make a marginal correlation between x2 and y higher than the correlation between x100 and y. So in this situation, you need a lot of features in order to you need to include a lot of features in order to include x100 there. And then, I could make it worse, making our condition, the condition that I talked about failed. So if I have a linear regression model here, I could always choose beta 4 such that the marginal correlation between y and x4 equal to 0. So in this case, if I use my correlation learning to rank the feature, x4 will never be selected. And this is the same happened in like a classification, right? So if instead of observe y, in this case, y and x4 are independent because everything here is normal. So instead of observe y, if I only observe the indicator of y, So then Z, that is the class, class label, and X4 are marginally independent. So there's no way that you are able to pick up by using two-sample t-test. So, the same way, I illustrate by this simple example here. So this is, Jianqing, and I have class 1, I have 10 patients. One is red, green, the fifth one is red, the sixth one is green, patients, right? So this is, and this is class 2. So if you use color, red as classifier, you have a little bit, you have a little bit classification power because there are 11 red here and 9 green here. So let's say just 45% error rate. And if you use Gen 2, which exactly half are red, half are green for class 1, and exactly half green and half red for class 2, so your misclassification error would be 50%, right? So there's no discriminant power between for Gen 2 to differentiate between class 1 and class 2. However, if you use Gen 1 and Gen 2 to make a joint decision, then actually it's very powerful. So if you look carefully, class 1 Gen 1 is always the same color, right? So class 2 Gen, they are always different colors. So if you use, let's say, the same color or the sign multiplication interaction between these two, then the joint decision have misclassification only 1 out of, which is this one, 1 out of 20. So it's, let's say, 5% error rate. So apparently this kind of problem cannot be, cannot be made by using the, the correlation learning or sure independent screening. So what we did here is, repeatedly apply the two-scale strategy. So first, from very high dimension, you apply, let's say, sure independent screening to, let's say, from, let's say, 20,000 or even 2 million to, let's say, your sample size is 200. And for this moderate scale, you could apply, let's say, SCAD, then Z selector, or lasso, or anything you like. So you go from here to here, and you come here. Okay, and so you, after you're doing this, you got residuals. So you could apply the same procedure. So again, you choose, you get residuals. You apply large scale by doing like a sure independent screening or correlation learning, and then apply moderate scales and so on. So and this way that you could improve possible the results. So here is a little bit detail of the methods. So this is a model scale of a model selector. So most of model selector admit these forms, right? So you have least squares and you have penalty on this side. And so one of the popular choice probably is L1 choice, so it's called lasso. And what make L1 even more popular due to very creative algorithm called LAS. And of course there are other modifications around those lines. And along a different, a similar line of thoughts that is on myself, I call smooth absolute deviation errors. And in many papers that we have shown that smooth absolute deviation error have much better mathematical sampling property because the penalty function we use here is flat at the tail, so which essentially implies that when the true parameter is, let's say, 5 standard deviation above 0, you don't really need to, penalize further, and because of that, so you have a much better bias property. And at the time of course 2001, I don't know the loss existence, right? This is actually Peter Billman's comment. I like that. So of course there's no loss existence. So we use local quadratic approximation, and now with the existence of loss, actually the smooth absolute clip absolute deviation error can be solved by a sequence of lasso or loss algorithm. That is. If you do local linear approximation, that is given initial values here, instead of approximate your loss penalty function by a quadratic function, you approximate by an L1 function function. Then this would be then you could solve the problem by using loss algorithm. So in other words, the numerical problem of SCAD actually can be solved by using a sequence of penalized L1 likelihood, but then you're getting a better bias property. So in that sense, the scat or whatever the function here, p lambda here, really dictate the schedule of your, let's say of your, the derivative of this function actually dictates how much you should penalize the parameter, because the slope there is really the L1 penalty that you use. How much weight is really like a weighted lasso that you use here. So the slope here really dictates how much you should penalize. And another class of estimator, very creative, by Emil Candet and Terry Tao, which basically says that is a Danzig selector. So you find your estimator along around the maximum likelihood, which is, in this equal to 0 is really the normal equation. Around the likelihood, using L infinity norm, and you find the sparsest solution, and they show the results within like root 2 log p mimic the orgo. So this I regard this as a moderate, dimension, the moderate scale model selectors. So if you let's say solve a problem of 20 million or 10 million and so on, you will have some issues of computation, or you have issue of estimation accuracy and so on. Okay, so now for a particular example that we are doing is using iterative application of SIS, which is correlation learning, ranking by correlation, and the SCAT. So in other words, from 10,000 dimension, I do correlation learning. I narrow down to let's say to 100, and among 100 parameters, I apply either penalized. We apply penalized smooth absolute deviation error. So I got let's say maybe among those many of those 100 features. Among those 100 features, many of those are 0. Let me say that I select 5 of those are non-zeros. So I have residuals, right, based on these 5 features that I select. So it's a large scale followed by a moderate scale, and then I could use SCAT-SIS applied to the residual again, right? So among these, I have residual. Regarding my residual as a y, I apply correlation learning to screen the features again, and once I screen the feature, I apply this again, and so I could keep iterate until certain kind of let's say recruiting schedule is stopped. And here is a few toy example just to show the improvement of this kind of idea. So this is one example. I have 3. Let me just skip this one. Let's go to this one. Okay. So the second toy example. So this is one example. I have observed y. I have 4. 4 features that relate to y, and the dimensionality p could be 100 or 1,000. And I designed my x4 in such a way so that the marginal correlation between x4 and y is equal to 0. So in other words, y and x4 are equal to 0. And so if you, let's say, now what I'm counting here, let's say for sample size n equal to 50, so I choose among 1,000 dimensions, I choose the first 49. I choose the first 49 most important features. In other words, I choose n minus 1, largest correlation, and so this is the subset of features I'm selecting. Among those, I counting how many of those actually including the true variable x1, x2, x3, x4. In other words, how many times I have sure screening among 50 features. So I rank this according to the correlation learning, and then I counting how many of those, let's say 49. Each time I have a model of 49 variables. Among those, how many of those contain x1, x2, x3, x4? So in other words, from 1,000 dimensions reduced to 49 dimensions, I have sure screening. So if I just, because the marginal correlation here is 0, x4 and y is 0, so sure independent screening, one pass have no chance of picking this. And interestingly, in our numerical experiments, we also got 0 for lasso. And if I use iterative application of SIS, I got 100%. And this is another similar example. I just adding 1 weak variables x5 here. Now again, I do, let's say among 1,000 features, I select 69 features, and I counted number of number of time I have sure screening, and that is number of more, in a thousand simulations, I don't forget how many simulations. How many of those it contain x1, x2, x3, x4, x5. So there are 0 for lassos, 0 for cis. If I use iterative method, I have 100% success. And there's a good reason, mathematical intuition behind that, but since the time is limited, so let me not explain further. Now, natural question people may ask is, how do we extend this to classification? And that is, how can I apply large scale followed by a small scale to the classification? So in this case, I have I have let's say misclassification loss. If I have linear combination of features, I have observed y. I have misclassification loss such as SVM or adder boost or logistic regression. And our goal is to find a sparse beta that minimize or minimize the loss. And so how do we do that? So if you really want to do that, the cis is very easy to do, right? So sure independent screening is very easy to do. That is, you just find, you just use marginal regression and using one single feature, trying to minimize the error, and then you got your omega j, and you rank you rank your feature according to your omega j or according to the reduction of the loss, which more generally is according to reduction of the loss. So you could just rank them and select n divided by log n variables. So this part is easy. Just doing marginal regression, you could do this for any of those loss functions. Now, the second part is that how do now I select a submodel, let's say of 200 or of 100 variables. So now I apply a moderate scale methods, that is penalized methods. So to select a further sub feature. Now after I doing this, maybe I got 5 features, and along with those, let's say 5 loading, let's say factor loadings or feature loadings. And so here what we do is, pre-screening only use the marginal correlation as we said before. And now the next step is, how do I reiterate the procedure? In other words, how do we define the residuals for non-quadratic loss? And and this can be this can be extended. So if you really just fix the first part, untouched, and then just adding a new feature in, you are asking yourself whether by adding this new feature in, how much loss being reduced. Then you could again rank this according to, let's say, the variance, the loss reduction, and you result as let's say a submodel M2, and you could keep like a large scale, large scale, moderate scale, large scale, moderate scale. So keep recruiting the features, so you could get your final model. And this is ongoing work that actually I'm doing here with one of my former students, and probably with Richard Samworth here. So we haven't got numerical results here, but it's basically an extension of the classifier that we did for like iterative cis2 classification. So I have talked a lot, so let me quickly summarize what I have talked so far. So because there's a lot, it's very easy to get lost in the whole, big forest. So we studied the impact of dimensionality on the classification. We quantify exactly extent to which how signal contribute to the classification, and how noise dimensionality contribute to the classification. And we introduce a fair method to select a feature, which using 2-sample t-test, and to select a number of features. So we basically shown that the high dimensional classifiers behave like a random guessing unless signal is very strong, because noise accumulation could overwhelm the signal. And we showed that 2-sample t-test could pick all relevant features as long as feature is 1/3 of order n to minus 1/3 away from 0. But still features need to be ranked and selected, because using all features not necessarily give us any gain. And we basically say that fair mimic well in comparison with Oracle ranking. we introduce the iterations for classification. Sys or iterations is a large scale followed by small scale. So speed up variable selection geometrically and also reduce the estimation error geometrically, so that you don't really have a log p penalty you need to pay as long as you have sure screening property. And in the development we talk here, sys and iterations can be combined with any well-developed model selection methods, just like a plane can be combined with any brand of car to drive you to Berkeley to provide powerful methods in high-dimensional variable selection. And with all those notes, let's say thank you.
A few minutes for questions.
Okay.
One of the issues with gene expression data is that each gene has got a different scale, even though they're measured on the same chip, but I didn't see how that was factored in.
Okay, so actually in the, when we do ranking genes by two sample t-tests, actually I do, in that sense, I do scale them. And there's another implementation. Sometimes people standardize features first and then apply classifiers. Sometimes people maybe do this in the scale. So the scale is automatic here on the way of doing the analysis.
I've got one quick one. When you motivated the sure independent screening, I think I got that right.
Yeah.
You used the regression of y on x, and then you appealed to a ridge formulation. Could you not also motivate that by using the inverse regression of x on y?
Inverse regression of x on y.
A linear model, just as you did, only put x on the left-hand side and y on the right-hand side.
Okay.
And that would yield the two-sample t-test directly.
So would that give me the what I call correlation learning? Let's see. It could possible. Yeah. I just say I haven't thought of. Let me see. Oh, sorry. No, not this here. Yeah, here. So you said that if I use y as x,
Put y on the right-hand side, x on the left-hand side,
right.
and then simply run down coordinate-wise through the x's, you get the two-sample t-test.
Oh yeah, oh sure. Yeah, that way certainly you could get that. Yeah.
In your method, you, if I understand correctly, you use the same training set both to choose the variables and to eventually build your classifier. Now, how do you know you don't overfit? I mean, in machine learning, sometimes this is done by splitting the training set into two parts.
Yeah. So you mean I'm using this to select a feature, and then later on I use this. Actually, in the situation I'm doing here, and at least the particular thing that I'm doing here, really I'm using the data just to select a feature. So once the feature is selected, then the whole classifier is fixed. So once feature is selected, then the whole classifier is fixed because I use independent rule, just like Fisher discriminant rule or MySpace rule to decide. So
but any classifier uses the same data to build the classifier.
Yeah. So I use the same data to select a feature. So once features are selected, then the classifier are fixed in the thing that I'm talking about here. And I understand what your concern about, like, of overfitting. I think the overfitting is more. In this case, there's only one tuning parameter I'm choosing here is the number of features, because once features are ranked, the test distances are fixed because it's just a weighted distance, and so I'm selecting the number of features. So number of features I'm selecting this way probably have a secondary.
The way I see it, you take the same noises twice. Once when you select the features, and then when you build a classifier.
Yeah, yeah. So as I said, the classifier really I'm just ranked by the feature. Once it's really I'm just whether you are using how to say it, whether the two sample t-test or something is big than certain threshold or smaller than certain threshold. Beyond that, actually, I didn't use much of to build a direction. And I mean, interestingly enough, I know you may ask me that after direction is being selected, and actually you are hinting at a question after let's say you and I agree to use 100 let's say features. Once feature is selected, now what is the optimal direction to use? Right. So among 100, I have one direction. Among 80, I have another direction, and so on. So this is a very interesting question, and actually, interestingly, it's connected very well with like a finance, like a Markowitz, like optimal portfolio choice. Actually, we are currently developing. The two mathematical problems are equivalent. But as far as what I'm doing now, really, I don't use much of the direction, choosing the direction now.